So today we're going to do our last example on chapter 17.4, which is equation of motion, rotation about fixed axis. And I have to go through, 1, 2, 3, 4 more examples on equation of motion, general plane motion. Okay, so that's what I'd like to cover today. So overall, we are going to do at least 3 examples. Hopefully, by doing these examples, it will cement your understanding of the topic better. Can you all hear me at the back, or it's muffled? Are you good? Right. Some of you, I see you guys less than 12 hours ago. Not a good thing, okay? Okay. Last night and today. Is it 12 hours? Yeah, or less than 24 hours. Okay. So these are the examples I like to do. Okay. And the last 3 example over here, this one over here, this one over here, and the guy going around in the wheelbarrow are some of the worst examples you can find in the homework on this topic. Okay. So let's go back to this example that I've started yesterday briefly, but let's do it over again. Now all these are loaded on Avenue to Learn. If you want all these questions and images, please go to Avenue to Learn. Right. So we have a boy sitting on top of a large wheel, which has a mass of 40 kilograms and a radius of gyration, kg, of 5.5 meters. If the boy essentially starts from rest at theta is equal to 0, and the wheel begins to rotate freely, okay, so the wheel is able to rotate freely. Determine the angle at which the boy begins to slip, the coefficient of static friction, elaborate over here, static friction between the wheel and the boy is 0.5. We're going to neglect the size of the human in the calculation. So I'm pretty sure you all know the difference between static friction and kinetic friction, yes or no? One is static friction is coefficient of friction measured when you want to move something. Kinetic friction is basically an object is already moving and there's friction. That's what we call kinetic friction, right? So we're going to calculate what we know first. So the mass moment of area of the wheel, IO, is equal to mk squared. These are the low-lying fruits, okay? So we only consider 400, and the radius of gyration is 5.5. Okay, so this we are focusing on the wheel for now. Okay, so 400 times by 5.5 squared, you got 12,100 kilogram meter squared. Okay, so that's what we know. Right, then the rest of the stuff we have to start constructing. We have to analyze our free body diagram. Okay, we're going to look at the free body diagram. So on our free body diagram, how the boy or how the boy will fall off or accelerate is in this direction. Okay, right? So this is how the boy will fall off, and it's about fixed axis. Then we have over here our t, and our N axis. Okay, so we're going to analyze this system over here, or how this is going to behave based on the E and N axis. Okay. So now we are going to look at the forces. I'm going to call the center over here O. Okay. So we will have OY over here. We have OX. And then we know the boy that's coming down over here. Not coming down, but we have a load over here. This load over here is equal to the boy's weight is 40 kilogram times by 9.81. So this is basically equal to 40 times by 9.81, 392.4. And then from here, we know we can resolve into two directions. Okay, so over here, this is our theta. So this will be our 392.4 sine theta. This is due to the weight of the boy. And the next one over here, this is your 392.4 cos theta. Okay. Then the next thing we're going to consider anything else. Now, so the next thing that we have, just by looking at a wheel, right, we know that we have a load pointing the opposite direction. This is our N. And then we have FF. Okay. So take note. FF will be effective okay when the boy is about to sleep. Okay, when the boy is about to sleep, then you have your FF. Okay. Then from here, we have nothing else to look at. Okay. Then we are going to again construct our kinetic diagrams. So when we construct kinetic diagram, what we do now is we know that this is rotating about an axis over here. And this is our I naught alpha. The boy, if he were to slide off, right, over here, so this will be equal to M A G E, and this is basically equal to M alpha R. And then over here, we have our M A. I don't know why I call G. I don't need to call G, okay? So it's not the A N. Okay, so over here, the formula we're going to use is M omega squared R. Okay. So the first thing we are going to consider, the case where theta is equal to 0 and before the boy starts to sleep. Okay, before the boy starts to sleep. Okay, so i.e. when boy, so for this case, okay, when boy is not sleeping, when the boy is not sleeping, okay, and we can use A is equal to alpha R. Okay. So in this case, we are going to look at when the boy is not sleeping. Okay, there's no motion. So the boy and the wheel are as one. Okay, there's no sleeping of the boy. Okay. So from here, we are going to take moment about point O. I'm going to start on a new page. Okay, I let you guys finish copying first. You guys finish copying? Okay. So I'm going to take the moment at point O. Okay. And then we are going to do summation about moment at point O in kinetic. Now that for this case, there is a very strong reason why we do that. Okay, I've tried other ways, and it does not. The working seems to be ridiculous. Okay, so this is the best way. And why we do that? Okay, why we do that? This is the only case I've seen after doing so many examples. This is the only case why we take moment at point O, so that do not know the reaction or do not need to consider the reactions OX and OY. We can drop them. Okay, we no need to consider them at all, and that's the only reason. Yes. No, OY are the reaction. Hey. We do in the mass moment of inertia later on the right hand side. Okay, so for this case, I ignore it, okay, in OY and OX. Okay, that's why I take the moment at point O. I don't need to worry about it for no reason. You have to remember, when the boy is rotating, OY is changing also. Okay, so for this case, I totally don't want to consider that effect at all. Okay, that's the only reason. Okay, so for now, we're going to take moment, anything that's anti-clockwise. So we're going to take moment at point O. So the only thing that we need to consider is 392.4 sine theta. So minus 392.4 sine theta multiplied by this. So over here, this is a value of 8. Then this will be equal to minus. So next is I naught alpha. So minus I naught. So 400 mk squared. We did calculate mk squared. So mk squared is equal to what? Mk squared 12100 alpha. Okay. And then we have to consider our boy. So minus by 40 times by our alpha, which we don't know. we know that the radius is 8, and we have to multiply another 8. Yes or no? 8. So both of these are the radiuses. So let me clarify something. So let me write out the formula. So this is equal to minus